Cool, right on time. Hi, everyone. My name is Sarah Conway. I'm a software engineer at Crunchy Data. I'm excited to be discussing with you today an open source project that my company has developed called the Postgres operator for Kubernetes. Just a small heads up, I do have a sore throat, so if I start rasping towards the end of the talk, I am very sorry. But before we get into the subject we're all here to talk about, I'd like to briefly talk about my company, who's responsible for creating this project. Crunchy Data is a leading provider of trusted open source Postgres and enterprise Postgres technology, 24/7 support, training, and custom development. We have a presence in the federal government space, and we are also the provider of Crunchy Certified Postgres, which is an open source Postgres 10.5 distribution, including popular extensions such as PostgreSQL and enhanced audit logging capability. This product is currently the only open source database that is common criteria certified at the EAL 2+ level. Our company is full of world-class Postgres experts, including core developers, committers, and major contributors. Our Crunchy employees are also responsible for developing and or contributing to the development of many community projects such as PG JDBC, PG Backrest, PG Audit, PG Department, and others. We're also hiring for a ton of different positions, including DBAs, system engineers, Postgres and container experts, and much more. Please feel free to reach out to us if you're interested, and I encourage you to take a look at our website at crunchydata.com. So for those of you that have viewed previous sessions on this subject, please be aware that there are substantial changes as to how the operator is built and what it's capable of in the last 6 months alone. While the first half we'll be finishing up today's session with a word to the wise, pointing out the brand new features in the last release of the operator, if you're not quite there yet, so you know what you're missing out on and where we're headed with it, along with what to expect in the upcoming release. The Postgres operator project is available in a fully open source repository on GitHub. This repository contains all the source code and has links in the README for documentation that goes into detail on how the operator works, along with command line syntax and examples. Please open up any issues on GitHub if you come across any bugs or if you have any requests for features for upcoming releases. This helps us to continue actively developing the project and push it in the direction that our users want. The operator is a controller. Basically, it's a shortcut for a Kubernetes or OpenShift cluster. It's an application for a specific component implemented on a per namespace basis that controls and manipulates Postgres deployments and centrally manages each graded cluster. Once the operator is deployed for the first time, the command line interface sparks basic Postgres operations through changing custom resource definitions. The Golang library Cobra and the Kubernetes client API for Golang, which is called Client Go, are used to build the operator. Client Go allows for direct interaction with the Kubernetes API with customized code to perform various management operations, such as creating, deleting, scaling, or automatically failing over Postgres clusters. The command line interface provides a very straightforward method for interacting with the operator. From that perspective, it works very similarly to the kubectl or OC command in that it allows you to directly talk to the Kubernetes and OpenShift APIs. Information can be received back from the cluster through PGO, and objects can be created instantly. And you do have the option to do additional troubleshooting commands through kubectl or OC interchangeably as well, so that you're not limited to just that one tool. And currently, the command line interface is the primary means for the operator to understand what you want it to do and to allow you to manipulate your clusters. However, as I will discuss and demo a little bit more later on, we are in the process of developing a graphical user interface for the operator. For those who don't care to use the command line interface or who prefer or like the option of a visual interface. The operator is executed as a standard Kubernetes or OpenShift deployment within your environment. The deployment creates 2 containers, one for both the API server and the operator itself in a single pod, in addition to a replica set to assist with replication. After it's deployed, the operator is going to sit, wait, and watch until changes occur on custom resource definitions, and these are defined to manage Postgres deployments. CRDs are a customized template-based approach for allowing users the ability to define the makeup of a Postgres cluster. Recently, I think about version 1.5 or so, Kubernetes switched over to these in place of third-party resources. They're just a means to catalog and store metadata and interact with the operator through the API. The Postgres operator is designed so that you can add your own set of templates that meet your particular requirements for your deployment. When you first initialize the operator, you'll notice that there's the basic CRDs that are created, but no definitions are there by default. And over time, as you create clusters or backup jobs or upgrade jobs, you're actually going to see new definitions added in that you can then monitor to watch the status of these tasks. And finally, TLS and basic auth security was added in relatively recently. And starting in release 3.0 of the operator, you can now define operator roles. The administrator role and read-only role is enabled by default, but they're considered to be samples. And you can configure those better to suit your security requirements as necessary. Complete documentation can be found in the configuration segment under installation on the website in order to learn more about how to manipulate the file and the created roles used for interacting with the operator. The operator is deployed by default to the demo namespace on the Kubernetes cluster. Again, this is configurable upon installation. It will manipulate and create all Postgres clusters in the same namespace it was deployed in. By default, the operator pod includes 2 containers, which is the operator itself as well as the REST API server, but it can include up to 3 if you include the web user interface. And as I said before, it's still in beta. The command line client for the operator does run separately from the cluster, such as on your local computer, where you can then interact directly with the operator. By default, when you create a cluster using the operator with the initial settings, you create 5 components: a primary cluster deployment, a persistent volume claim, a persistent volume, and a primary service. This can get wildly complicated as you add things on over time. For example, you could define that you want a metrics pod to be added and a PG pool, say 3 replicas, by default, every time you create a cluster. You can also add in, like PG Badger and PG Backrest as well. It's important to remember that even if you enable all additional objects that I mentioned before to be created as part of this cluster, you have the ability with PGO to manage all of these as one single basket of items. Typically, you'd have a struggling DBA who is either creating scripts to do all this creation and management of these components or is doing it individually, each component at a time. At a large scale, or even if you have particular requirements as to how a cluster needs to be set up, this can become unmanageable from a developer perspective. This is the huge value of the operator that allows you to do wildly complicated tasks with single commands, and it essentially simplifies Postgres clustering mechanics. And as I mentioned before, you can modify the default definitions for what gets created, as well as append on or add on additional components after creation. The default definitions are written in a configuration file called pgo.yaml, which I'll go a little more into detail for later on in the talk. I've touched lightly on the advantages of the operator, but I'd like to go a little more into detail on exactly why it's useful. It's absolutely possible to build templates for deploying various components at once, or even to create and manage everything individually. We even have another project called the Container Suite that's just that. It's a template-based approach to deploying Postgres clusters and performing various DBA-related tasks on the clusters, all using JSON and YAML and various scripts, as built-in documentation and plenty of examples that make it simple to run more than 30 different administration scenarios. Well, the operator is built pretty much just right on top of that. While the suite is more of a manual project that requires you to do the heavy lifting, the operator fits right on top and does the heavy lifting for you. It has the huge advantage in that it can automate database workflows easily. Examples of this include backing up and restoring databases, upgrading them, or scaling up the number of replicas. Automation reduces human errors and allows you to manage, allows you to manage large numbers of Postgres containers without necessarily having to build your own set of scripts around the base level containers to do specific tasks. Without automation, large numbers of complex database deployments are extremely time consuming, and the operator is able to consistently enable workflow automation. You then have standardization across your project, with advanced users being able to define a standard set of database objects that can be created instantly by default, or specific SQL-based policies that can be applied upon creation. It allows for very specific needs, such as being able to categorize databases with metadata labels, or automatically populating newly created clusters with predefined tables, indexes, and data. It's also pretty straightforward to use. Not only is the command line interface simple to use, with the syntax improving with every release, but the PTO command line tools focused entirely on managing a set of Postgres clusters That means that database users can focus on getting their own work done without needing to become their own self-sustaining DevOps team with explicit and advanced knowledge of Kubernetes. It's not required to use the kubectl or OC commands to manipulate the clusters. The ability is simply there for the DBAs who want that additional level of control. And as you probably guessed, the operator is optimally suited for large-scale deployments. It's great for managing hundreds of databases all at once and allows for collecting and maintaining metadata on all those clusters, and it gives the users the ability to query based on that data to ensure that database assets are being usefully managed. It's fast. New clusters can be provisioned in a matter of seconds. It encapsulates the complexities of managing databases into a uniform package. Rather than taking a long, complex series of steps to upgrade a database, you run a single command that generates everything for you. And this process lends itself to a separation of concerns. It breaks down to the concept of microservices versus macroservices. Everything is relatively lightweight, providing for high-density deployments. These highlighted features show what was kept as a primary focus while the container suite was first being developed. As I mentioned before, it's built on top of the containers from that project, from the Crunchy Container Suite, and these features were used to design every Postgres container developed in these. It was designed to first address the high demand for a streaming replication environment, and it used to be an incredibly complicated process to set that up, especially in a consistent manner. So having the ability to do that easily was important to the design process. This includes the ability to have both synchronous and asynchronous replicas. Multiple locale support is built into the container suite as well, straight into the Docker files. And then you have secret support. In Kubernetes and OpenShift environments, you can store secrets to your database using kubesecrets. A nice feature specifically for OpenShift is the ability to use a random user ID for the Postgres user rather than using the default. And that's one example of using wrapper code inside the Postgres container. And then you have flexibility of what you want to do with that Postgres image, such as being able to backup and restore using PG-based backup. And finally, with each minor or major release for both projects, we always make sure to add support for the latest Postgres version and fully test that all features work as they are meant to. This set of base containers are the building blocks used by the operator to behave and work to deploy Postgres. The operator has different behaviors that it does that are based off of 5, I guess more now, looks like about 10 different containers out of that whole suite. Crunchy Postgres, Backup, Backrest, Upgrade, PG Pool, PG Badger, Collect, Grafana, and Prometheus. These Docker images are all fairly self-explanatory, but I will go over them more in detail when we go over the actual examples of the syntax itself. It can actually work with specific images and examples out of the container suite as well. So if you wanted to enable a Crunchy Collect container with your pod, you would then go to the container suite and have it work with the Crunchy Metrics example, which will allow you to deploy Prometheus and Grafana as metrics graphing tools. And over time, we are looking at expanding out this list to include other images from the container suite. And here are some quick links for reference before we get into the command line syntax. These links, as well as a link to the slides, will be provided at the end of the presentation, so you can either snap a picture of these for later or just a slide link at the end so you can access these. These are all the base requirements to run the project. We, of course, always recommend the latest stable version of all these components, but these are the minimum tested versions for the operator. This is especially important where it comes to Kubernetes and OpenShift due to the disparity between third-party resources and custom resource definitions that I mentioned earlier. If necessary, earlier versions of the operator, such as version 1.5, can be found in the repository under the relevant tag, and those are built using TBRs. It just won't have the latest features of the operator. And as follow-up information related to that note, we are looking at versioning our docs for the operator and the container suite, so that it becomes much easier to deploy earlier versions of the software if necessary, and know how it works and how to interact with it. On to the commands. The create cluster command is easily the most flexible out of any other with the PGO command line tool. There's a huge variation in what's possible with this one command. First off, you have the -e or series flag, which will allow you to create multiple clusters at once. So for example, if you wanted to say PGO create cluster test series equal to 3, it'll create test 0, test 1, and test 2. Next, you can specify labels in your clusters that can be nested. So for example, we could define a label of labels equals project equals earth, and another cluster with labels equals project equals Mars. You can query your clusters for everything within the folder or label project, which would show the results for both Earth and Mars. Or you could look for those specifically labeled Earth. I will be talking a little bit more about what policies are later on, but the light version is simply that they are a SQL-based file of certain parameters that you want your database to be set up with, such as indexes or tables to be created upon initialization. You can apply them to clusters after creation or during the creation process using the policies flag. You can set an initial password for use by the default created database users, as well as append a metrics collection container to the cluster with a metrics flag. This is the Crunchy collect container, which includes the Postgres exporter and Node exporter open source packages for scraping your Postgres container and grabbing database and operating system level metrics to deliver to whatever graphing or aggregation agent you prefer. As of the latest release of the container suite, we now include native support for something called PG Monitor, which includes a customized Grafana dashboard and default statistics to show you the connection counts, database size, replication lag, transaction wraparound, load levels, and system metrics. Custom config allows you to override the default pghba.conf and postgresql.conf files by using the flag along with the name of a config map that holds your customized Postgres configuration files used to override the default. You can also specify the cluster name to use when restoring secrets when bringing up a cluster from a backup with the secrets from flag. CCP image tag specifies the version of Postgres, the container images, and the operating system type to use for the cluster. The default in pgo.yaml is simply the latest stable version of Postgres in the container suite, but if you want to specify an earlier version for just one individual cluster for some reason, you can definitely do that, or vice versa. So for example, if you had a bunch of clusters running 10.2, you could create a new test cluster with the latest version 10.5 using that flag to just test everything out. Backup path and backup PVC flags specify which backup archive path and persistent volume claims to restore from when restoring from a backup. Then you have pgpool and pgpool secret, which respectively allow you to append the crunchy pgpool load balancing container and optionally separate pgpool secrets from, that are different from the default configuration. Again, added in the last 2 releases or so, the crunchy pgpool, pgbadger, and pgbackrest containers have been added from the container suite to work directly with the operator. pgpool provides load balancing through a smart Postgres-aware proxy connected to a Postgres cluster to both the primary and the replica, so that applications only have to work with a single database connection. The pgbadger utility is provided as an additional monitoring capability, as it generates a Postgres log analysis report using a small HTTP server running on the container. And then you have the pgbackrest container, which executes pgbackrest against the cluster while allowing full and delta restore capability. It's fully configurable through the pgbackrest.conf file. The pgbackrest utility was added in the latest release, 3.2, and it's still considered to be an alpha. At this point, it's just essentially meant to give users a preview of what is to come. So we're looking at some extensive improvements in 3.3 and 3.4. The ability is present to do a manual failover of the Postgres clusters, but there's also an auto-fail flag that will let you enable automatic failover for the cluster. Additionally, you can enable archive logging to be enabled for the database cluster with the archive flag. This allows for recovery of the cluster if necessary by restoring the file system backup and replaying from the archived WAL files in order to bring the system to a current state. The 2 storage config flags allow you to respectively define the name of a storage configuration variable that is defined in the pgo.yaml file to use for either the primary replica storage or the replica upon cluster creation. As a reminder, we'll be reviewing briefly how to do these things later on in the slides. You can also define the resource configuration to use, again defined as a variable, that holds specific CPU and memory requests and limits. And finally, you can define the node label to use when placing the primary database. Without setting this, any node is going to be used. With this command, it's almost the equivalent for the kubecontroller OC get all command, except the primary difference is the show cluster command will show all components of the cluster, specifically to what you're querying, including the pod, service, and any added-on components such as replicas. It's also going to show any policies or labels applied to the cluster, what Postgres version is being used, and other management information specific to the operator. It will also show the status of the pod, whether it's running and ready, And you have the option to either show a specific cluster or query for all clusters that were created by PTO. You can also apply for other objects such as a backup or the contents of a PVC or a policy. And I will review the content covered by show user later on. This output that it generates can be translated into JSON or YAML output, and you can query based on labels that we defined at cluster creation or later on applied to clusters. You can also query for clusters matching a specific Postgres version. Say you have like 5 clusters that are 9.6 and you want to know exactly which ones those are so you can upgrade them. Just look for the Postgres version. The delete cluster command allows you to delete all the components except for the persistent volume claims and the backups by default, all in one fell swoop. If you run the delete cluster command against a cluster or a selection of clusters by itself, it will leave those PVCs and backups intact in order to preserve those very important things from accidental deletion. Because, it'd be a little bit awkward to explain, how it just so happened that you took all the data and the backups and just threw them into a fiery dumpster. Especially because the workflow for backing up and restoring a database or upgrading it is to first drop the containers, but work around the PVCs and just upgrade the data. However, if you are serious about deleting everything, you can still happily toss them into the fire through the delete data and delete backups flag. If you don't want to feel guilty about it, just throw in a new no prompt flag. And that's going to prevent the confirmation message that's asking you, hey, are you actually sure about that? And as you might expect, it's possible to delete other objects as well, such as created policies, upgrade jobs, users, or backups. PTO Tests will allow you to test a specific cluster or clusters, matching a selector. The output will print out the connection status, the equivalent pSQL commands, and the database IP address for the Postgres, master, and standard user accounts. It's a very simple SQL query test that allows you to verify connectivity and ensure everything is running and connecting as expected. If you have it skilled with additional replicas, each replica would be tested as well in the same manner. This also goes for the creation of any user accounts that are connected to the cluster. Each would be tested as well as a separate connection for both the primary and the replicas. Krei Policy allows you to create a SQL file and give it a common name within the PTO management system to assign it to clusters. This is useful for a few scenarios, such as if you have a series of SQL statements you want to apply to several databases as a Postgres user. These can be security-related, application-related, or even specifically to simply create a common set of starting database objects. Really anything you'd like. Essentially, they're just pieces of SQL that you want to name and apply to a single cluster or all clusters, actually, or a selection of them. The SQL will get applied and run on the Postgres database by the Postgres user by default, though you can always define a specific user inside of those SQL statements. The flags tell the command where to find the policy file, either from a local or remote location. After creating the policy, you can then choose to apply it to either an individual cluster or against a selection of all clusters that match some specified criteria. This can be especially useful if you have 100 or so databases that need to be updated with a new security policy, for instance, as you could run PGO apply against the entire suite with one command. You could also apply policies with a dry run flag, which will then test and make sure that which cluster the policy would be applied to without actually executing the SQL. User management has been refined within the last few releases of the operator in order to be more flexible with what it's capable of. You can now use PGO create user and PGO delete user as commands to add or remove users. And PGO user is the general management tool for all other user management-based queries. For example, you can regenerate the password for a user using Kubernetes secrets, grant a user access to a database, show the passwords that will expire in X number of days, create a user with Kubernetes secrets that can be managed by the operator, update expired passwords, and set passwords for new users to expire in a certain number of days, which by default passwords are going to expire every 30 days. The managed flag will be especially worthwhile to note, as users added without the flag enabled will not be able to be manipulated by the operator. For example, if you create a managed user, you will now be able to test connections to the database with the user using PTO Test. You can view the generated passwords, and so on. There's many more combinations of these flags that you can do to orchestrate your users exactly how you want, and more features are being added every release. So definitely check out the documentation here and experiment with the different user creation methods. In previous versions of the operator, there used to be a show secrets flag that was appended to the show cluster command. That's now been deprecated and replaced by the show user command, which is run against the cluster in question or a selection of clusters. The output of this command will show all associated user accounts created and managed by the operator for the cluster in question, along with their passwords generated through Kubernetes secrets. Labels can be applied to clusters and nested according to their type, with any string input being valid. As of recent releases of the operator, you can now additionally delete labels that have already been applied, as well as do a dry run of the application to make sure that only the correct selection of clusters are being labeled with your new label. And just as a rehash, you don't have to actually define a specific label name. You could, if you want to, you could define a label as being a projector, and then list a whole bunch of projectors under that. You can choose any name you'd like. PTO load works similarly to the policy commands. Essentially, this lets you load a CSV file into the database. The loading is based on a load definition found in the sample load config YAML file under the examples directory. It's documented how to run it, but essentially in that file you have the data to be loaded, and when it's executed, jobs are created to perform the loading for each cluster that matches the filter. The reload command will perform a PG control reload on the specified Postgres cluster. To be more specific, running PG control reload will simply send the Postgres server process a SIGUP signal, causing it to reread its configuration files such as PostgreSQL.conf, PGHBA, and other similar files. This allows you to change configuration file options that do not require a full server restart to take effect. Starting with release 2.6, there is now a manual failover command, which can be used to promote a replica to a primary role in a Postgres cluster. This command will perform all the heavy lifting for you for executing a manual failover by first choosing a target replica to become the new primary, deleting the current primary deployment to avoid user requests from being executed to multiple primary databases, promoting the targeted replica using PG control promote, causing Postgres for the replica to go into read-write mode. And finally, it is going to relabel the targeted replica to use the primary labels that will match the primary service selector. This will allow new requests made by the primary to be routed to the newly elected primary. Because it involves the deletion of the primary deployment, you will be prompted for a command line confirmation once again that yes, you really do want to delete this deployment. You can avoid it with the no prompt flag. The query flag will give you the full list of failover candidates, so that way you can specify a specific target. Postgres is considered a single primary database by design, so by default, you'll have the primary deployment set to a replica count of 1, and it's not going to be able to scale beyond that. However, you do have the ability to create any number of replicas that can connect to the primary, creating a streaming replication Postgres cluster, in which all the replicas are read-only and the primary is read-write. The PTO scale command will let you scale up the number of replicas in the replica deployment. The service created for this will also perform round-robin load balancing to the replicas. The deployment is created by default for the replicas, with the actual number of replicas upon creation being set to 0, but this number can be changed in the configuration file to automatically provision, say, 3 replicas every time you create a new database cluster. Otherwise, you can manually scale up the cluster using this command. Right now, these replicas are asynchronous by default, but we will later on be adding in support for synchronous replicas. Additionally, you may want to note that previous to 3.2 of the operator, it was not actually possible to scale down the number of replicas that were created, but that feature was now just added in order to let you selectively delete certain replicas if needed. You can also specify a specific version of Postgres for the created replicas if for some reason you need it to be different from the default set in your configuration file. You can double check that everything is working correctly from a Postgres standpoint, of course, by connecting to the database using pSQL and checking the PG stat replication table if you're running through these examples in smoke testing. You have the option of upgrading existing clusters between minor or major versions of Postgres in addition to upgrading the container version itself being used. It uses the crunchy upgrade container from the container suite in order to execute the PG upgrade utility against the cluster. It will request confirmation for the command when executed, as the procedure for upgrading an existing cluster is for the operator to delete the existing containers of the running database and recreate them using the specified image tag or the new default definition specified. The database files themselves will not actually be touched during the upgrade, as once the upgrade is complete, the operator will create a new database container with the newly upgraded PVC, which contains the upgraded data files. You can keep watch on the status of the upgrade by viewing the status of the PG upgrades custom resource definition that's created by default. And depending on how large your database is, this operation could take a while. The PTO command will let you see the disk capacity of a cluster's PVC versus that of the Postgres data that has been written to disk. If the capacity is less than 50%, then the output is printed in red in order to alert the user. It also will print out the name of the cluster, the status, the size of the data directory, the total capacity of the PVC, and the total percentage used of the PVC. You can use the PTO status command to see the overall status of the operator itself. Selective metrics are displayed to provide some insights to the Postgres user and the administrator as to what's running currently in the namespace related to PTO. Specifically, it'll let you know what time the operator started, the total number of databases, backups, and persistent volume claims, along with the total volume size, what database images are in use across the entire cluster, and any databases that are detected as not being ready, as well as any applied labels. Finally, it will display node information for any linked Kubernetes nodes in your environment, along with their status and labels. And of course, the two commands will be the best for you, those of you just beginning and experimenting with the project, will be the PTO version and the help flag. The PTO version flag will show both the version for the operator and the API server, and the help command can be appended to any combination of the above commands for help on the go. Now, a large part of working with the operator is having the ability to configure everything that's done by default. This can be a huge time saver if you have a consistent method of how you want your clusters to be deployed, and it also provides the basis for other command flags we've covered previously, such as the ability to select predefined resource or storage configuration names. This file is located under the conf/API server directory by default. You will find all this in the documentation. The first segment, cluster, deals with the default creation criteria for all new clusters, as you might expect, including some default parameters for new users. This is where you're going to change the information if you wanted your clusters to be enabled with the PG Badger container by default, for example, and you want them to have 5 replicas. Now, a brief explanation of strategies. So each strategy supplies its list of templates used by the operator to create new pods, services, and so on. When the operator is deployed, part of the deployment process is to copy the required strategy templates into a config map that gets mounted within the operator pod. The default strategy template includes everything we saw earlier, which is a deployment running a Postgres primary container with a replica count of 0, a service mapped to that, a replica set with a service map for that, and a PVC for the primary if not specified in either the configuration file or a flag passed into the command. As of release 2.5, you can now define n number of storage configurations within the pto.yaml file. Those storage configurations follow the conventions of having lowercase unique names. They can then be referenced in the configuration values for backup storage, replica storage, and primary storage. While those are used by default, you can, of course, define your own. So if you wanted one for disaster recovery storage, you can define that name and then map a storage configuration variable list to that and reference it in your flags that you define when you create new clusters. You can set the storage access mode values to one of 3 values. The first is read-write-many, which mount the volume as read-write by many nodes, read-write-once, which mounts it as read-write by a single node, and read-only-many, which mounts it as read-only by many nodes. These storage configurations are validated and are only read when the PTO API server starts, and if a non-valid configuration is found, it will abort. You then have the size for each PVC in addition to the storage type. There are going to be 4 possible values right now for a storage type, and the first is dynamic, which allows for dynamic provisioning of storage using a storage class. So this will be used if you have Gluster or Google Cloud Environment, any of those. Then you have existing, which allows you to use a PVC that already exists. So for example, if you have an NFS volume mounted to a PVC, all Postgres clusters can write to that NFS volume mount via a common PVC. When set, the name setting is going to be used for it. Then you have create, which allows for the creation of a new PVC for each cluster using a naming convention of cluster name -PVC. And when set, the size and access mode settings are used in constructing it. And finally, you have empty dir. If a storage type value is not defined, this will be used by default. This is the volume type that's created when a pod is assigned to a node and exists as long as that pod remains running on it. It's deleted as soon as the pod is manually deleted or removed from the node. You also have 2 optional values you can specify for the storage configuration section, which is FS group and supplemental groups. FS group can be set in order to cause security context and FS group attributes to be added to pod and deployment definitions. And the supplemental groups setting will cause a security context to be added. There are some values not defined by default in the file. For example, if you wanted to automatically apply any policy you create, you can define in the configuration file a policy value under cluster and set it to the names of policy values that you want applied by default. Finally, you have the PTO-specific settings. You're not going to need to modify these too much, but it's worth noting the following variables. First, if auto-failover is enabled on the cluster, you're going to want to note the auto-fail sleep seconds parameter. It defines the number of seconds to wait for the primary database to return to a ready status within the timer period. If it fails, a failover will be triggered by the cluster by auto-failover logic. Audit is a Boolean variable. If set to true, it will cause each API server call to be logged with an audit marking. This gives more in-depth logging on each request you make to the API server. Finally, you have the CO image prefix and CO image tag settings, which define the container version to use with the operator itself. You'll just want to note that the number changes with each release, obviously, so when you're upgrading, this is where you're going to change that variable. I mentioned this command briefly earlier, but you may want to note it, especially after the context of the previous slide. This will display the running operator configuration parameters that are in use. So this is where you're going to make sure that the changes that you just made are current and working as you've expected them to be. A lot changed in the last release, so I'm only highlighting some of the major features added in 3.2. Specifically, we now support PG backrest as an added container, whereas before the only backup type supported was PG-based backup. PG Boundary was added in, as well as PGO reload, and you can also define your Kubernetes service type to be used, such as toggling between cluster IP and load balancer. Upcoming, there's a lot in the works. We have PGO OSB, which is an implementation of the Open Service Broker API, and this works with the operator in order to provision services. It allows users to bind to a service instance, actually, such as a Postgres cluster, which when invoked will return the login credentials for the database to a user they can use to connect to the database instance. Next up, we have PGO UI, which is a GUI browser-based interface for the operator. This is also still definitely in alpha, but will eventually become a full-fledged interactive dashboard for those of you that may prefer to more graphically view and interact with the operator. We're also working on integrating Kubernetes ingress with the operator, which is an API object that manages external access to the services in the cluster. It can provide load balancing, SSL termination, and name-based virtual hosting. And finally, we're looking at the ability to clone at the disk and database levels. This is a preview screenshot of the operator GUI. This is still definitely a beta design as well. It will be undergoing a complete redesign in the next few months, in addition to be brought up to date with the latest features of the operator. Eventually, it's most likely going to be included in the operator package by default, maybe just enabled as a separate feature. As a summary, I'd like to reiterate some of the highlights of the operator and what the true goal is for the project. Essentially, what it's achieved is the ability to securely provision databases at a large scale in a structured, reliable, stable environment by working with Kubernetes. Clusters are created as deployments that have full disaster recovery capabilities, in addition to being highly scalable and highly available, and having the ability to be deployed to any cloud platform, including Amazon Web Services or Google Cloud platforms. You can then also instantly provision databases that have all the requirements necessary to meet the most complex compliance requirements within seconds, without repetitive work to configure multiple databases at a large scale. It all comes down to the simplicity of managing your Postgres clusters in an open source, straightforward manner. Here's all the contact information and links you should hopefully need. That's my email there at the top if you have any questions following this talk. Jeff McCormick is the lead developer and architect behind the project. So if you're interested in seeing a particular feature and need to know more specifically how something works, he's going to be who you want to talk to. And if you're interested in working with Crunchy to deploy the operator within your organization, please contact either Robert Bates or Paul Lawrence. I did shorten the link to the slides to make it easier to type out, but I will be linking this to my personal Twitter account, as well as on the official Postgres Open website under slides. The official repository for the project is found under GitHub, and we do offer documentation as a separate GitHub pages site found on that link there. And finally, if you're wondering how to make awesome slides like this, please check out Reveal.js, which is a fantastic resource for building slides. And that's everything for me. Thanks. Any questions?